So good afternoon, everyone. Welcome to the QCRE webinar series. So today we're lucky to have Dr. Hui Yang to give a talk. So first, let me briefly introduce Dr. Yang. Dr. Yang is a professor of industrial and manufacturing engineering and also bioengineering at the Penn State University. And he's affiliated with the Penn State Cancer Institute, the Clinical and Translational Science Institute, the Institute for Computational and Data Sciences, and CIMP 3D. Currently, Dr. Yang serves as the PI and the site director of NSF Center for Health Organization Transformation. Dr. Yang was the president of the IISE Data Analytics and Information Systems Society from 2017 to 2018. And he was the president of the Informs Quality Statistics and Reliability Society from 2015 to 2016. And Dr. Yang was also the program chair of the 2016 IISE Annual Conference. He's also a department editor for IISE Transaction Healthcare System Engineering and associate editor for IISE Transaction, IEEE Journals of Biomedical and Health Informatics, IEEE Transaction on Automation Science and Engineering, IEEE Robotics and Automation Letters, and Quality Technology and Quantitative Management, and also an associate editor for proceedings of IEEE Case, IEEE EMBC, and IEEE EHI. So without further ado, let's welcome Dr. Yang.
Thank you, Dr. Fang, for the introduction. So today, I'll welcome everybody to this webinar. Today, I'm going to talk about sensor-based modeling and optimization of additive manufacturing. So, here there's a affiliation called SIMS 3D. SIMS 3D stands for Center for Innovative Material Processing, actually 3D printing. So this project is primarily collaborated with SIMS 3D. And also today's talk will be primarily based on this paper, Six Sigma Quality Management of Additive Manufacturing, which is a review paper summarizing a series of papers in the area of quality assurance, quality control of additive manufacturing. So for more details, if you are interested, you can dive into this paper to know more. So why can we get together today in person? Because it's complex because of the COVID-19. However, Zoom gives us the flexibility. Now let's get together virtually. So special thanks to Dr. Xiaolei Fang and Dr. Na and Dr. Lin Kanbian, the president of QCRE Society, and also QCRE, all the board members and the community for the opportunity to present for me to present my work in this webinar. So in the beginning, I would like to thank my research collaborators. So I have learned so much from my research collaborators on 3D printing. So Dr. Prahalad Rao is my academic brother, and he's well-known in 3D printing. And Dr. Simpson, Dr. Simpson was the director of SIMS 3D. And as you may see, this is actually a 3D printed statue of Dr. Simpson. So, so now you can see what 3D printing can do. It looks like a real person. And Dr. Yan Liu from LIST and Dr. Ted Russo from SIMS 3D and Dr. Paul Vizero from LIST, Abdallah Lazar from SIMS 3D, and Dr. Sandar Kumara, and also my advisor, Dr. Satish Pukapallanam. Yeah, without their support and help and also guidance, and my research work would not have reached this far. And thank you very much to my research collaborators. So at Penn State, I run a lab called the Complex Systems Lab. So my research focuses on sensor-based modeling and optimization of complex systems. So applications including manufacturing and healthcare. So no matter it's a manufacturing system or healthcare system, and we have sensors like IoT sensors, Internet of Things sensors. Previously, we called it wireless sensor network. And then if you connect those wireless sensor network to the internet, it will become IoT-enabled sensor network. And those sensors collect a lot of data. If you have thousands of sensors, it will become supervisory control and a data acquisition system. We also call it a SCADA system. So SCADA is widely used in the industry. No matter it's hospital, power plant, chemical plant, manufacturing plant, and we use those sensors to increase the information visibility and also address the system complexity. But advanced sensing brings big data. So how in industrial engineering, we focus on sensor-based process monitoring, modeling, and analysis, including system informatics and control, data analytics for knowledge discovery and decision-making, and also definitely quality and reliability engineering. And also you can leverage those data to calibrate computer models and doing the computer experiments and simulation optimization. In the reliability side, of course, you can use the model to do the prognosis, maintenance, and optimization. So theoretical foundation is actually, I focus on the nonlinear dynamics. So this is something that is a little bit, I want different from majority of the researchers in the IE field. So I focus on the nonlinear dynamic system theory, statistics, and the signal processing, simulation, optimization, and control theory. Those are the theoretical foundations to support the sensor-based modeling and optimization. So also, I would like to thank my research team, and they are really the people who behind those work and research work. So my students, this is a picture we took in Seattle, and I happened to have a chance to meet with all of my students. They are all the students in my lab. I happened to see that group. Then we took this picture. And many of them have been tenured associate professor and tenure track assistant professor. And some of them, they are working for industry as well. This is another picture with my healthcare colleagues and at the hospital. And I went to the hospital and tried work with them on the healthcare problems. And we had this picture together. At Penn State, I also supervised the senior design and undergraduate research. So those are, this is a picture with undergrad students. And this is also a picture with my undergrad research students at my lab, Juan Gomez. And he is a Schreier honors student. And I'm very glad to have an opportunity to learn from my students, also has the opportunity to work with them in the research project, leverage the research project, really build the successful development of my students and their career. So now let me get into the additive manufacturing. So additive manufacturing provides new design freedoms. As you can see from this picture, it make it possible to fabricate those complex geometry products, and which was not possible if you use the traditional manufacturing, for example, the subtractive and machine cutting, and it's impossible to reach such complicated geometry. And also, if you see the top right, you see there's an icon, right? That's my hand actually holding a ball. That's a nested ball. Within the bigger ball, you will see a smaller one. Those kind of structure can only be done through the additive manufacturing. So additive manufacturing provide a faster speed to go from the design. If you have an idea and design idea, you can put it in the CAD model, and then you can go with the materials processing steps and put it in the computer or 3D printer, and you can print the part. And also it enables mass customization. So mass customization means that for some of the times, if you do a product with 3D printing, you might only print it once with that. Not like the traditional mass manufacturing. Mass production is you have the same design, you produce thousands, millions of them. But now 3D printing allows you to have the flexibility to produce only one part. We call it We often call it one-of-a-kind manufacturing. And because of the complex geometry, sometimes it offers expanded function application. And the speed actually reduces the life cycle cost. So for those who is not very familiar with additive manufacturing, let me give a brief introduction of what is additive manufacturing. So if you have a design and you cut it in the layered sequence, okay? And then you put this design into the 3D printer. And then you use a coater to spray a layer of the powder. It could be metal powder. And now you use a laser to fuse those powder together to form one layer, okay? Once you finish this layer, you're going to load down the powder bed, and then you spray another layer of the powder, and now you fuse it again. Then layer by layer, layer upon layer, you will be able to get the final part, a final build. Okay, this is a laser powder bed fusion process. Once this is done, and you sweep the powder off the powder, the bed, and then you can get the final part out. So this is a 3D printing. And this video is a brief version that is available in this YouTube link if you are interested. So as you can see, if you have a design idea, and traditionally you need to go through conventional manufacturing supply chain. You need to go through the prototype phase, and then manufacture system. You need to build the manufacturing or production system. And then all these products will come to the distribution center. And there will be the warehouse to store those. And then it was transported to the retailing store. And then it will reach the end customer. But additive manufacturing gives you the flexibility to bypass the traditional linear supply chain. And if you have a design idea, you can submit the CAD model and you can get it printed somewhere with a supplier. And then it will get mailed back to the end customer. Okay, so this is another paradigm. We call it manufacturing as a service. So MaaS. As you can see, becomes two-sided market. You have manufacturers, additive manufacturing manufacturers, and you have providers, and you also have customers. So customer with the design, they can come to the online marketplace, and the provider just mail them back. So about this manufacturing as a service platform, and how do you enable the sharing economy of additive manufacturing? So we know that we have Uber, right? And all this like DoorDash and all this like sharing economy and Airbnb. But what about manufacturing? Can we enable a sharing economy for manufacturing? As we can see here, we call it manufacturing as a service. So this is one paper about our idea, how to use matching theory to realize or to implement the sharing economy of additive manufacturing. So matching theory is the Nobel Prize winning theory in economics. Now, can we translate those kind of theory to manufacturing and make a better manufacturing system or manufacturing world? So if you are interested in sharing economy and manufacturing supply chain, and you may refer to this paper. This is just published in the past month. So this is not just talking. And as you can see here, Penn State has about 20 major campus. So it's a Commonwealth campus, not just located in UP. UP University Park is the main campus. But we have 20 more Commonwealth campus distributed in the state of Pennsylvania. So in this paper, what we're trying to do is to build a digital fabrication network. So for example, at UP, we have NAND building, IST building, all these buildings, they provide FDM, additive, powder bed, additive, and metal printers. And also we have traditional subtractive manufacturing, okay? And how do we provide this kind of service to all the students? So the students can submit their design and get it processed somewhere in the UP campus or other campus. And then once the part is manufactured, they can be shipped back to the students, okay, through the campus mail. So this is called digital fabrication network. And this is a small version of sharing economy, but which is implemented in the Penn State system. But think about it, we can extend this to the whole United States or to the whole world. So additive manufacturing is wonderful, but there is a great challenge, which is quality control. And which will come to the industrial engineering, also come to the IISE QCRE division. And we have so many researchers working on the quality control. But additive manufacturing, we did a case study at Sims 3D. And this is from Andrew Coward and Dr. Simpson. So we use the same CAD model, the same machine, okay? And we print 7 parts in the same bed, okay? Same time, but very different results. Okay, only 2 out of 7 were built defect-free. And the others, they have different kind of problems, the internal defects, or you have problems like in this layer, or you have malformed things. So the process has a very big variability. Then how do we overcome this kind of variability? Quality control, can we just print and pray, as my colleague, like Dr. Prahalad Rao said, and should we just print and pray, or we should have a better control method? And this will come to the sensor-based in-process control. And those kind of defects, they cause functionality problems. You know, fatigue failure of a powder metal oil conduit in a Qantas airplane, Airbus A380 jet engine. And November 4th, 2010, Qantas Flight 32 caused big problems in the engine, actually blow the whole engine into the building and cause serious damage. So the problem is caused by a 3D printed part with internal defect. Because in the aircraft engine, they need to have very complex, like a fuel to be injected to the compressor. And they have complex design. And if there's an internal defect, then the fuel we got some problems, and then the engine got blown away. So this caused serious problems. This is an example. If the quality is not well controlled, what kind of damage it can make. Now, before we really get into the quality control, and let's first define what is quality and what are the challenges in the quality and reliability in additive manufacturing. So let's follow the 6 Sigma AM. First, we define the quality challenge and also the customer requirements. So for example, FAA application, which will be different from a traditional consumer application. And the measurement, how do we measure? If we define the challenge, how do we get the data? How do we, what kind of sensors and what kind of metrology measurements should we make? Now, if we get data, how do we analyze the data to extract useful information? So we call this DMAIC. Then if you analyze the data, you got insights, and then we can improve doing the design of experiments or doing the simulation model or computer experiments. And then we can plan the process and optimize the quality management. We can control the process. So in today's talk, I will go through each block. So first block is define the quality challenge. So what is the quality challenge? What's the difference between traditional manufacturing and additive manufacturing? So traditional manufacturing, like the mass manufacturing, it's high volume, no mix. So high volume, no mix means you produce a lot of parts, they are identical to each other. So now, if the same process manufacture many parts, they are similar to each other, then for example here, part 1, 2, 3, 4, and to n. And then it's very much easier for you to quantify and have a distribution. And then you can quantify the variability. And then you try to design experiments to really reduce the process variability or machine variability when they produce the parts. Quality, when we define quality, quality is inversely proportional to variability. So here we have data and we have high volume product that can give us flexibility to quantify the variability. And then we can reduce the variability. But the challenging in additive manufacturing, sometimes it's a one of a kind of manufacturing. So one of a kind of manufacturing means you only produce one. Then how do you quantify the variability? But fortunately, even for the same part, and you build many layers, right? So each layer can serve as a quality inspection point. And then you have more data that can enable you, the quality or variability study. So as I write here, AM, or 3D printing, offers the design, the flexibility to customize design, and allow you to do the low volume and high mix production. But as you can see, there are layer-wise geometry differences in the 3D printing. So, but if we can do the in-process sensing and layer-wise sensing, or even if you do the laser like fusion, you have multiple and point-wise sensing, then you will have a lot of like a flexibility to do the quality control and quantify the variability of the process. For details, you may refer to this paper. So let me give you guys an example. What is the quality challenge? For multi-layer AM build quality, if the probability to contain defects is 0.0114 in a layer, then what's the probability for this layer to have no defects? So this is about 1% there is a defect. I mean, if it is 1%, then 99% there is no defect. So it's 98.86. Pretty good on one layer, but is this good enough? For AM build with 100 layers, if every layer, the probability is like this, okay? What's the probability for this build with 100 layers to have no defects? Then every layer have to be like containing no defects. So this will be your power 100. It's about 31%, 31.77%. This is about true, right? 2 out of 7, they're defect free. And so now you see the challenge. For a build with 100 layers, the probability to fail, then use 1 minus this, then 68.23% the probability to fail. So if the probability of build to have internal defects is, if you wanted this is a 68% to fail. That means a very large probability it will fail. But if you wanted to failure probability to be less than 10%, then what should be the probability for a layer to have no defects? Then you can solve this. Actually, you have to reach 0.0011% for one layer to have no defect. So this comes to the 6 sigma. If you want to realize that, you have to have 6 sigma AM quality management. As you can see, if we can achieve 6 sigma, and you see plus minus 3 sigma is 99.73%. If you go to 6 sigma, plus minus 6 sigma, it will be 99.999 and 698%. So parts per million defective, and this will be the layer defective. It will be very low. So now we have gone through the quality challenge in AM that is different from the traditional manufacturing. Now, how do we measure the data, and what kind of sensors do we use? So the engineering problem, this is by courtesy of my colleague, Dr. Prahalad Rao. 1-inch tall miniature turbine blade takes over 3 hours to do the X-ray CT. But FAA mandates every AM part to be qualified. So it takes time and a lot of money to qualify a new part, use purely empirical testing. Okay, so this is a post-build. And also in the post-build, if you find problems, you cannot really fix it in the process. You have to scrap the part, and that will be producing that will have a lot of waste if we can only do the post-build inspection. So an alternative solution is in situ sensing and quality control of the AM part, qualify as you build. So AM. So you have design phase, and then you have material. So material, we need to qualify the material because you have powders. Make sure the powder, the distribution, how to characterize the powder, what kind of characteristics of the powder. And also powder requirements for the suppliers and the reuse. How do you reuse the powder? Because you see we sweep off a lot of powders. And you also see we have process. Process is a system qualification, especially the sensing technology and process monitoring and diagnostics. And after you build the part and we have the product, we also need to do the performance qualification. So you can do the post-processing, like thermal processing, post-process finishing. And then we also need to do the post-build inspection. So now in this talk, I'm going to focus on the middle part, the sensing technology and process monitoring and diagnostics. So if we do this material process products, then it will come to the adoption implementation. So at Penn State Sim3D, we have integrated an advanced multi-sensor suite into a commercial 3D system ProX 320 PBF. PBF stands for Powder Bed Fusion AM system. The sensors include the imaging system and high-speed, high magnification cameras, and high-speed video, and optical process emission, acoustic sensors. And here we also have thermal imaging. So this is a thermal melt pool. When you use a laser to fuse one point, this is a melt pool that you build. It's like a mountain, okay, like a volcano, right? So in Earth, we have volcano and form a particular geometry and of the mountain. Now in the 3D printing, we also use the laser to fuse a specific point, and it will generate a mountain and a melt pool as well. So those are the system design with acoustic sensors, spectrum sensors, high-speed video, and the layer-wise imaging system. So this is by my colleague, Dr. Russo. So now let me dive into the high-resolution layer-wise imaging for improving process reliability. So this is a 3D printing metal PBF system. And we have the control unit and DSLR camera. And we also put you see here, the proximity sensors. So every time when the recorder come back to this point, we take a picture. Before printing, after printing, we take a picture. And this is a picture we got, example picture. And we also have thermal imaging, so you can get the thermal image. And you can compare whether there are spatters and the image is what the melt pool is conforming or not. And you can digitally build up the images, layer-wise images, and then you can see the quality. So this is a part built for Honeywell. And you can see the distortion leads to additional powder bed anomalies. And this is a system design of the thermal camera and also the layer-wise imaging system. So those are the sensing. So sensing, there are different ways to do the sensing, and there's thermal imaging, optical imaging, and those kind of advanced sensing and imaging system, they generate a lot of data. Now the next step is to analyze those data, extract useful information about the process, and understand where the variability is from, and also perform root cause diagnostics. So if there are data, we talk about data enabled smart manufacturing. So from the data, we want to extract useful information and derive the insights and the knowledge, and then gain a better understanding of where the variation from the system, and also like you do better control and better actions, and there's a wisdom in it. So in each phase, we have different kind of algorithms, data, insight, and action. But when it comes to the data, and people use AI. So AI is a hot buzzword, and no matter what we do, people say AI. And also there are many AI institutes. AI stands for artificial intelligence. And so what is the different culture between AI and engineering? So they do have different cultures. Engineers stays with machines, systems. So what we are trying to do as an engineer, we try to understand the data, extract useful information, and then we optimize the process, systems, and organization. Computer scientists, they deal with computers like codes and algorithms. So work on the computer codes to fit the data. Hopefully the codes will fit into any other data. So those are the different cultures. So it's like the Superman, right? So no matter what problems, people say AI. So like AI tell engineers, easy means I have got you. Engineers say, oh, you got me. Who has got you? Okay, so the real idea or answer is we need to really have interdisciplinary study, like integrate AI, data science with engineering domain knowledge. Okay. So if you only have AI without domain knowledge, it will not work. But sometimes if you only have domain knowledge, the research can still work. But AI or data science make the engineering models or engineering solutions much better. So that's why we need to connect and doing the interdisciplinary research and discovery. So if it comes to the engineering domain knowledge, we need to, that's industrial engineer, that we need to design experiments. Experiments help us to test the hypothesis and understand the system and process better. So for example, this is a powder bed, and this is a build plate. So in the build plate, we have cylindrical part, we have different geometric part, and the blade, engine blade. We also have fin pad. So this is a thin wall structure. So for cylindrical part, you see the power. Laser power we have at a zero level is 340 watt, but we vary it by like 25% or 50% reduce and or above. And the scanning velocity, so V0, and then we have minus 25% or plus 25% and plus minus 50%. Also, there is a hatching space. Hatching space can be bigger or smaller, but with this impact, how and whether those parameters impact the final build. So these answers, engineers, we need to do experiments. It's not like you get a deep learning can figure it out, right? So this is engineering domain knowledge and engineering solutions. And also, if you build a thin wall means it's a wall, and with different thickness, different height. If you build a thin wall with different heights, sometimes because of the weight, it can tend to crush the below layers. So in this design experiments, we have different thickness of the thin wall or width of the thin wall and different height of the thin wall. And also you can see the thin wall are placed in different directions. So this arrow direction is the recoater. That means every time you finish a layer, you recoat the powders in a new layer, and then you fuse it again. You see, we place the thin wall in the same direction as this is 0 degree as the recoating direction. You can do 60 degrees, and you can also do 90 degrees vertically, right? And then how does it impact the final build? So those are the engineering design, and also you design the thin wall in different ways. Now, engineering design, you see recoating directions, 0 degree, 6 degree, and 90 degree. And they also have different widths, different hatching space, different height. You also have different hatching pattern. So all these parameters will impact the final build quality. So this is an image of the final thin wall build. It's a wall, right, with different height. You want to see, if you want to quantify the process variability, you build such things to see how this impacts the final build, whether it collapses or not. So this research actually is summarizing this paper. So if you are looking for more mathematical details, you can dive into this paper, which is a recurrence network analysis of design. So you have different designs, and then later you got different quality. So design quality interaction in additive manufacturing. So you have LPBF machine with different thin wall build. Now you can do the image registration, combine the CAD and put it on the top of the XCT. You register the image and see each thin wall and what is the quality inside the build, inside each thin wall, and whether there are discontinuities or there are different kind of quality features, and how do they relate to the design parameters like the height, width, and different process parameters. So this is the DOE and the modeling, and this is recurrence network to quantify the build the data, and then we try to build the relationship. Okay, and so for more details, you can dive into this paper. Now let's have a look at the in situ sensing for AM defect characterization and estimation. So we can characterizing the defects in the post-build CT scans. You can also link the process condition with defect characteristics in the final build. And there are also process level, like in situ modeling, okay, in process modeling from the layer-wise image. So we want to build the connection between process conditions, sensor signatures, and the defects. So this work actually is summarized in these two papers. And we studied the multifractal characteristics of the image profile to characterize and detect the defects in additive manufacturing. And also, how do you go from process condition to build quality through the modeling and the monitoring of in situ layer-wise image. So those are the more details. Now let me give you a little bit like information about multifractal analysis of in situ AM image profile. So this is a AM machine, and you build it layer by layer. This is the excess powder, and when you use a recoater to spray this layer, excess powder will come here, and then you lower down the powder bed, you fuse another layer, okay? And this is a build component, a cylindrical part, and you can characterize the CT scan image. You can get the CT scan. And now we can analyze the CT scan, try to see the multifractal spectrum. And then you can do the image guided, like a Hotelling T-square, and to do the statistic variation modeling. And then it is defect detection, defect characterization, and optimal design. So here we look at different things, which is called multifractal characteristics. So in the next few slides, I'm going to introduce what is a multifractal analysis. So multifractal focuses on the rough and irregular patterns over multiple scales. For example, if you have a powder bed, if you zoom in again, this shows some kind of patterns and similarities, okay? And how do you quantify those kind of activities? So this is a complex systems approach, and which is well known from Mandelbrot, okay? And fractal characteristic of fractal surface of metals. Fractals is actually everywhere. So in this study, we actually divide the build each layer into multiple scales. Then we look at the, we call it the Voronoi cells. So Voronoi cells inside each scale, we look at what is inside this build. And then we look at zooming again, we zoom in again. Then we look at those characteristics and see how those patterns vary with respect to the scale. So this is basically the idea. We want to quantify the multifractal spectrum. So fractal is actually everywhere in the nature. If you look at the mountains, if you look at the trees, so it's a fall, and now the trees are turning yellow and red, the leaves, and it's very beautiful. But if you look at the leaves, you will see the multifractal patterns and a tree, different branches. So they have rough edges, and you see this peak is similar to this peak. And if you look at the overall, there's some kind of rough edges. And it's a non-uniform shapes. So fractal has been studied for last hundreds of years, and it's not as long as Euclidean. So Euclidean has been studied for more than 2,000 years. For example, the man-made structure. So like this building. This building is a Penn State industrial engineering building. They are man-made structures by civil engineers and civil construction workers. So they use the triangles, circles, squares, and all this kind of Euclidean geometry to build these man-made structures. But if you look at the nature and like flowers, trees, mountains, they all show some kind of fractal patterns, okay? It looks similar, but regardless of the magnification. And multifractal means it's not only one fractal, it's actually many fractals. Now I'm going to show you how fractal works. For example, you have a platform, right? Now you only do the middle point placement, displacement. That means this is a middle point, right? And then you also have middle point here. And now you're going to randomly displace the middle point. If you randomly displace the middle point, you will be able to see another structure here. And if you iteratively do it again in another scale, you will get a different geometry. And if you do it again, you got a different geometry. And this is the final mountain you may get. So fractal geometry is widely used in Disney, in Hollywood, to do those movies, especially they simulated the fire and also mountain, and especially they have some animated movie, and they use fractal to create all these structures that it's very, very vivid and very beautiful and very similar to what we have in the real world. And this is hardly done by the Euclidean geometry, but if you use fractal, it's very easy to generate such complex geometry. And in the nature, you also see something very fractal, like this is, you see the tree, the river branches, and they are very fractal. You see, if you zoom in, it's similar to what we see here. And if you have seen lightning before, there will be lightning also have the fractal patterns, right? And if you see the gravels, like those kind of structures, like a powder, and they are very fractal. And we did a simulation study. We randomly generated the points and see what kind of fractal pattern we have. You see, from random, single, and the single class matter and line, they all have different multifractal patterns. And when it comes to the CT scan, if there are defects, you will see multifractal characteristics are related to the frequency or number and the size of the poles. And you can see they can characterize these kind of activities. Now, if you have the fractal characteristics, those are the different kind of fractal patterns. And if we vary the process condition, for example, the power, if you minus 25%, minus 50%, and the velocity, you also, this is called scanning velocity, because the laser, when lasers start to move, they move in different speed. And in one line, they scan one line, and the next line, the hedging space sometimes may also be different. This kind of multifractal patterns, they actually show that if you have different process condition, your multifractal characteristics will be in different locations. So can we build a regression model, like predict, based on different process conditions to predict the multifractal characteristics? Yes, we can. And the R-square is more than 94%. So this is a model diagnostics. You see the residues, they are pretty normal, okay? So this is a first study and focus on the multifractal patterns in the additive manufacturing process. Now let me talk about AI. You see they all both have AI and AM. And so my students come to me and say, oh, why not we use AI? So we also have another build, which is a drag link part. This is a drag link part, and printed in Sim 3D with intentional defects. Intentional defects, that means those are the intentional defects. We have some kind of holes over there. And we have 4 layers, and we build those kind of defects in these 4 layers. And the diameter, cylindrical defects, like those are cylindrical defects, they have different diameters. And the cubed, and you also have cubed, and they also have different size, okay? So different shape and size of the defect. Now, if we have the layer-wise imaging, can we predict, because we know the ground truth, can we predict what is where is the defect and how large they are? And it's not as simple like you put the in situ image into the black box and it will tell you that, right? So I think many deep learning, when I read the papers, they put the image into the deep learning and then they try to get accuracy. And when I discussed with my team member, and I said, oh, you cannot just do that because every layer, you see, once you do the additive manufacturing, and you got a geometry variations, because this layer and the next layer, they have different geometry. If you put just the image into the black box, into the deep learning, then what's going to happen? And this layer, you have a powder area. You also have the have the geometry, the build geometry. But the build geometry changes. That means your powder area also changes. If you just throw the image into the deep learning neural network and then later AI figure it out, I mean, it's going to be very hard. So that's why what I'm saying, AI needs to be integrated with engineering domain knowledge. So then later I discussed with my team member, with my PhD student, I said, maybe we can use the CAD design to put it on the top of the image, and then we register the LI, because the region of interest is really what we are interested in. We are not really interested in the powder bed outside. We want to see whether this layer is okay. And then inside this LI, we can do the freeform geometry analysis in different ways. So LI segmentation with the greatest common divisor of the AM layers. Then every layer, and if you segment them into sub-LIs, they all have the same number of pixels, and with the great GCD of AM layers. Then this, now you can do the spatial characterization, and now you can put in the deep learning neural network. And this is this idea actually summarized in these two papers. And if you are interested in details, you may refer to these two papers. So far, I finished the analyze part. Now let's get into the improve part. Improve part is more about the understanding of the process, especially the AM ontology. So ontology, Bayesian network, so BN, and the causal discovery. We want to understand what is causal relationship. So only by understanding the causal relationship, we can improve the process and do the robust design. So AM ontology is a high-level map that is useful to explore and understand the interrelationships of parameters, elements, and variables during the AM process. So you have the QA. QA stands for quality assurance. QC is quality control. So QA, QC requirements. Every user has QA, QC requirement. Then we look at the ontology of the AM machine. Okay, ontology represents what engineers know about the process. That is a domain knowledge and also intercorrelations. We have sensor ontology. What kind of sensors to choose to sense a particular phenomenon? We also have machine and process ontology. That is a domain knowledge. But on the other hand, we have Bayesian network. Bayesian network is data-driven. We study the probability and the interrelationship, and then which can digest the sensing data. And then you learn the structure, learn the parameters. But how do you really intertwine or integrate both process? For example, then if you connect domain knowledge with Bayesian networks, that means you will connect the domain knowledge or integrate domain knowledge with the machine learning method. So then you can answer the questions such as what sensor to select, what are the root cause of defects. And this is one paper that we have recently published called ontology-driven learning. That means you have an initial network based on the ontology, and you also have data. Now you can learn from the data and also integrate the ontology knowledge, and then you generate a new Bayesian network, not just purely learn from the data. And then you do the causal inference and the quality assurance in additive manufacturing. And this is part of the project called Amazing. So here's Amazing. Amazing stands for Additive Manufacturing Analytics and Sensing using Intelligent Knowledge Graph. Okay, it's an amazing project. I had a lot of fun working with my colleagues, students, and also with my collaborators. So we can do a top-down approach or bottom-up approach. So top-down means users, they have QA, QC requirements, and they have different kind of application. For example, they want to diagnose if something wrong. They want to diagnose what caused this, and this is called diagnostic inference. And also predictive inference means if you know the process conditions, how do you predict what's going to happen? And intercausal, inside the process, what are the causal inference? And also mixed inference. If you have such applications, you can query the domain knowledge like ontology. And you can also use learning in the second box. Now, if you want to build the model, you have to have data, right? So you go to the demand database and then require the sensors and different type of data, discrete data, continuous data. And bottom up means you get the data, you put it in the database, and then based on the data you learn, and then you do the inference. So if we can integrate top down and bottom up together, and then do the AM analytics and sensing, this is an integration between integration of domain knowledge with AI and machine learning. So here, I also would like to give a shout out to my colleague, Dr. Prahalad Rao, and he did an excellent paper on graph theory and AM simulation. So the paper is listed here, like thermal modeling in metal additive manufacturing using graph theory. It's a very interesting paper and a very fast simulation compared to the finite element. So if you're interested in simulation, I strongly suggest you to read this paper. So step one, obtaining the geometry of a part and converting it to the point cloud. You see, you have a point cloud. Now you construct a network graph from the sample nodes, and then obtain the results as temperature array, which shows the temperature history of the part. Okay, and then you're hitting the layer hatch by hatch, diffusion the heat through the part, deposition of another layer. Okay, so this is a very creative idea to do the graph theory for the simulation. Yeah, this is a very excellent work from my colleague. And now Dr. Prahalad Rao is also having an NSF project try to commercialize this new simulation tool. And really amazing work from Dr. Rao. Now, so far we have talked about define the quality challenge, measure the data, analyze the data, and then improve the process. Now, what are the control challenges and how do we do the optimization of the process? So AM is very unique. You see, you have a layer upon layer decision making. So in layer T-1, so the state is high. This is a state action transition diagram. This S stands for state, A stands for the action. So SH, SM, SL denotes the high, medium, and the low defect state. So if you have a defect probability, there's a probability that this layer has defect. And then based on the state, you can take different actions. So you can, AW means that you wait and do nothing. And AL is like you can do the fix. You can come back and fix the defect part. And AM means small m, this M means machining the whole layer off, like hybrid manufacturing, additive and the traditional subtractive. You can actually remove this layer and redo it. This is different action you can take. But if you are in a state, you take a different action, you will have a series state action transitions. So different state, you choose different action. It will cause the subsequent state to change in the next layer and also the subsequent layers. The sequential optimization is that you have sensors and then you do the sensing and then you quantify the defect level and then you do we call it MDP, Markov decision process. You want every step to be optimal. So that's the Markov decision process for image guided additive manufacturing. So the detailed mathematics mathematical detail modeling details are available in these two papers. And we even consider the constrained Markov decision process. That means when you are making the decision, you are constrained by a lot of factors. For example, you cannot do the repair for every layer, right? You have a certain budget to do the repair. And then how do you, under this budget, how do you maximize the probability that this final build will have no defect? And when we characterize or quantify the defect state, there is a probability. That means the past layer and the present layer and the future layer, you have the mean and also you have uncertainty quantification of how likely is this layer to have a defect. And if you define the failure threshold, then you will have a probability that this layer to fail. So this is a sequential decision-making process. But first, we need to have a sensor-based model to characterize and quantify the uncertainty of the failure probability. And based on the quantification, for example, you have AM build, you have sensors. Now you can quantify the state. And the state will give you different kind of action and reward. And then the decision agent, based on the reward and the state that you are in right now, and then choose a new action. And then you continue to sense and state, and then reward, and then decision agent. So the decision agent stands for the MDP agent. So the state is a defect signal, and with uncertainty. Now, action you can take here, we consider two actions: take corrective action or wait and do nothing. because wait and do nothing is also an action, right? It causes subsequent behaviors. The cost is the cost of the corrective action and the cost of waiting. And if the final build failed, and then you have a failure cost, that's pretty high. So if you are in a particular state, and you can see you have state transitions, and once you get into a new state, you will have a value associated with a new state. And also you take an action. Now, this action also has a cost. But if the state is greater than the failure threshold, then you have a failure cost. So this is the optimal control policy we derived. And this work is done by Professor Bing Yao, one of my former PhD students, who is now an assistant professor at Oklahoma State. And she has done excellent work to consider the historic data and also sequential decision-making. And then he said whether we should take corrective action or we should wait. Okay, so if you are below this line and the policy is you wait and continue the observation. If you're above, then take corrective actions. And here is when you consider the failure cost and action cost. And sometimes failure cost is not that high, right? So compared to the action cost, then you will have you will have a different kind of levels of the control limit for different layers. This really depends on what is the cost and of the final build. If you have a very important or critical parts, your failure cost is very high. But if you have a consumer grade product, then the failure cost may not be that high. Okay, now let me summarize this talk. AM, additive manufacturing, provides new design freedoms. So previously, what do we have? We have subtractive manufacturing. We need to design to make subtractive manufacturing or traditional manufacturing possible. Because if you design very complex part, the manufacturing may not be possible, right? But now, additive manufacturing enable a new paradigm called manufacturing for design. That means any complex geometry, any complex designs, additive manufacturing gives you the freedom to manufacture them. So this is a paradigm shift from design for manufacturing to manufacturing for design. Design complexity makes quality control actually very challenging. And the complexity of engineering designs, we also need new qualification methods and tools. So in-situ sensing and online monitoring is one possible solution, actually, and compared to the post-build quality inspection. So realize the full potential of sensing data depends really on the new models and the new algorithms for sensor-guided AM. So this is what we proposed, DMAIC. Traditional, this is very classical IE methodology, methods and tools. But I think when we consider traditional DMAIC, DMAC, we didn't really consider those kind of in-process sensing or advanced those kind of high-dimensional sensing. And so DMAC can be extended to incorporate the advanced sensors. And we can study the design and build quality relationship interactions and characterize the defects, link process condition with defect characteristics. And then we can also do the process modeling and then the sequential optimization. So this is all the reference and relate to this talk. And if you're interested in some of the topics, please feel free to refer to those papers. And acknowledgement, and I would like to thank NSF and especially my career award and my colleague and my collaborators, my students, and NSF Center for E-Design and Sesame, NIST, Lockheed Martin. Lockheed Martin actually is the first company who sponsored the image-guided like AM project like about 5 years ago. That really got me started to study AM. So very much thank Lockheed Martin. This is my contact information. And I'm very glad to have this opportunity to talk with my fellows and friends, colleagues in the QCRE community. And I'm happy to answer any questions you may have.
Thank you, Dr. Yang, for the excellent presentation. So any questions from the audience?
Okay,
Yeah,
Dr. Yang, thank you for this inspiring talk. It's really eye-opening for many of us. So I think this presentation is already really comprehensive. So what do you think will be the next big problem in AM to solve? I think we have quite a few junior faculty or graduate students here. So I think they benefit. And I want to know personally a lot about your advice on that.
Dr. Lin, Dr. Ben, and it's a really good question, and also a forward-looking question because AM right now is a rapidly developing field, and also a lot of research ongoing in AM. I think AM really changed the traditional manufacturing paradigms and actually entering a new manufacturing paradigms. There are many issues to be, or many research questions that can be, should be, or will be investigated by many colleagues. I think it can also be well connected with traditional IE methods. When it comes to the AM, we see new challenges, right? So for example, traditional high volume, no mix, we have a lot of parts to quantify the variability. But when it comes to the low volume, high mix or one of a kind of manufacturing, I mean, it's very difficult for IE traditional methodology to be applicable to quantify such variability. And we have excellent researchers in the QCRE communities. And I think this is a great opportunity for us really to contribute. And because when traditional manufacturing gets started, and it started from mechanical mechanical engineering community, then I jump in and try to help, because we make things once we can make it possible, right? And now it's IE to make really improve the quality, improve the reliability, and make sure the production process, the variability is smaller, and we can have high quality part. So those kind of new challenges really really motivate IE industry engineers to think about how to develop traditional IE methods and tools, and then really develop them, design them, those new ideas, and then contribute to the additive manufacturing. This is not just limited to the quality engineering. If you look at the supply chain, if you look at the design of experiments, you look at the engineering statistics, analytics community, if you look at the OR, like operations research, how can we connect traditional OR methodology and also develop those OR methodology and then contribute to the optimization of additive manufacturing? I think that there are a lot to be done. And this presentation is just my 2 cents. My preliminary study in this area. I think many QCRE engineers and colleagues, they have excellent ideas, and I think they can really contribute to this field if they are interested additive manufacturing. Yeah. Now, there are many interesting problems to be investigated in this new manufacturing paradigm. So yeah, and if we can really implement and improve the quality of AM, I think the manufacturing is going to be different in the next 2 decades.
Thank you, Dr. Yang. I think that's definitely a $2 million, at least $2 million idea, more than 2 cents. But I appreciate sharing the thoughts with us.
Yeah, great.
Hello, Dr. Yang. Thank you for your talk. I was wondering if you did any work or looked at support structures and their effect on the part quality.
Oh, that's an excellent question. Did I interrupt you? Do you have further questions?
No, that's all. Well, I was just going to say, when I'm setting up builds, I always try to support more than less, just because I don't want a failed build. So I was wondering if you looked at strategies for that.
If you look at the thin wall build, actually, they have different kind of support. And because their width is different, then support will be different. If it's too thin, it's very hard to support at the top level, higher thin walls. So you will see the quality will be different. And that's one support structure for thin wall. And recently, we are also looking at the supporting structures for different geometry, especially, and then we look at the layer-wise imaging and also the melt pool, and with different kind of support structure, and how will it impact the quality, and also the geometry variations in the final build. That's a very good question. And it takes a lot of research efforts to really optimize and understand the support structures. But that's ongoing work, and also the one work on the thin wall actually considers the support structure. But that's also an open field. I strongly encourage you to investigate more. If you have interesting papers to share, please feel free to reach out to me, and I will be happy to provide my 2 cents or learn from you guys about supporting structure.
Of course, thank you so much.
Thank you.
So any other questions we have? It's already 4 to 6. So if there's no more questions, I would like to thank all the audience for joining us today. And this video has been recorded. We are going to share it using our QCRE social media. And finally, I would like to thank Dr. Yang again for this great presentation. Thank you.
Yeah, thank you, guys. And it's my great pleasure to interact with you guys online today. And have a wonderful rest of your day and the rest of your week. Take care, everyone.
Yeah, thanks.
Bye-bye.